There's a neat pattern in mathematics called the Babylonian Spiral. We start by dividing the XY plane into a grid of integers. So each of these dots represents an integer value in the XY plane. We're going to start at 0, 0 in the center. And we're going to move around this grid with two rules. The first rule is you have to take the smallest step that will end at a point on the grid. So we're going to go from 0, 0 up to 0, 1, because that's the smallest step I can take, a step of length 1 that will still end up somewhere on the grid. So I go from this point to this point. Then we continue that process, and you're always going to take the next smallest step that will end at a point on the grid. So I've already moved 0, 1, so I'm not allowed to move a length of 1 anymore. I have to go the next smallest length. The next smallest length is going to take me a distance of 1 by 1. So I move to the right 1, and I move up 1, and I end up at this point 1, 2. And so we're going to continue that process, always taking the smallest step that we can that will still end up on the grid. And when we have a choice of where we can go, we're always going to curve around counterclockwise. That's the second rule, always go counterclockwise. Actually, it's always go clockwise. The second rule we're going to follow is always turning clockwise. So we're always going to try to spiral around in a clockwise pattern. So the next longest that we can go is to move to the right 2. That'll bring us here. The next smallest that we can go is to move 2 to the right, 1, 2, and then down 1. So that'll put us here. The next smallest that we can go is 2 by -2. So we'll go over 2, 1, 2, and down 2, 1, 2, down into the negative, or the lower half of the XY plane. After that, we can go 0, -3. So I'm going to go down 1, 2, 3. That'll put me somewhere down here. Then we're going to go to the left 1 and down 3. So we'll go to the left 1 and down 1, 2, 3 over to here. And so you see we're getting this spiral pattern. It's kind of getting broader as we go along. Let's see, we did -1, -3. Now it's time to do -2, -3. So we're going to go over to the left 2 and again down 3. 1, 2, 3. I'm running out of board space. But fortunately, my next step is to go to the left by 4. So 1, 2, 3, 4. I'll end up over here. So I go from here to here, from here to here. And what you notice is that I start to take these very sharp turns, right? So it's a nice spiral pattern until I get this kind of very sharp turn there. Let's do a couple more to illustrate this. We'll go to the left by 4. So 1, 2, 3, 4, and up 1 over here. And one more, we'll end up going to the left by 3. 1, 2, 3, and up 3. 1, 2, 3. So somewhere over here. And so it's a pretty straightforward algorithm, but it doesn't always proceed nicely. You see, it's got these sharp turns. Like for example, here it's got this very sharp turn because the component you're changing suddenly switches, right? Here we're changing the x and the y. Here we suddenly go to just changing the y because that gets us the shortest distance we can go. Here we go to suddenly changing just the x, whereas we were changing the x and the y before. So we can put this into a code and see what kind of pattern it will produce. So let's see what we get if we put this in a Jupyter notebook.
The first thing we're going to do is create a function that will determine what our possible next steps are. Remember, we have this arbitrariness where we might go in any direction, but we have to pick one that goes in the clockwise direction. So the goal here is to find the next longest vector with integral endpoints on a Cartesian grid. That's the formal definition of what we're doing here. So first we're going to get an overestimate for the farthest we might possibly go in any one direction. So this is just going to be the square root of the last distance plus 2. That's going to be sort of the longest that we can possibly go, because anything farther than that we might as well just go an integer number of steps along just one axis. And so we're looking to minimize this next distance. And so we're just going to make it so high we can easily minimize. We're obviously not going to go 100 times the previous distance. We're going to go at most 2 more than the previous distance. And so what we'll do, we're looking for a certain number of steps in the X direction and a certain number of steps in the Y direction. And so that's what our N and M are, is to keep track of 2 different directions. So we're going to test out the distance of N squared plus M squared. And so the question we're looking to evaluate is, how does our test distance compare with the last distance we traveled? Because we need this next distance to be greater than our previous distance, because we've always got to go the next smallest distance that we can go. So this is going to immediately reject any step that is too short. We also need to reject any step that's too long, because if we've already found a shorter distance we can travel, then we will just ignore this test distance. So you notice we start out with this as a ridiculously big number, so it's automatically going to pick the first combination of N and M that we try out as a success based on this piece here. And then we'll keep going along and seeing how well that works out. So our next distance we're going to call our test distance, because we're saying, okay, this is the new minimum, so it becomes the new maximum that you have to get smaller than to beat. This is the current winner. And then we're just going to record that step so that we can compare it later and figure out which one we want to select later. So the thing we are going to return is this test steps. This is going to be the set of possible steps that we might go on. So our next steps, this is going to be the ones that we bring out of the function. And so what we're doing here is looking at whether this actually accomplished the minimum distance, because maybe we recorded one that was too long. Maybe we hadn't quite gotten the minimum yet. And so this is only keeping the best of the best, the shortest of the shortest, that also exceed the last distance. And so what we're going to return from this function is 2 things. First, we're going to return this set of next steps that we might take. And we're also going to return the next distance, because we're going to need to be able to feed that into this function and use it for comparison purposes later. So here we define a cross product and a dot product, because we're going to need those to evaluate whether our spiral is going clockwise or counterclockwise. And then we come to the main function where we actually create the spiral. We're going to create a spiral that is n points long. So we're going to specify the number of steps to take, and then the spiral will conclude. We'll start out at 0, 1, because we know we're going there. We know that our previous step from 0, 0 to 0, 1 was a step of 0, 1. So we kind of start out with the first step as a freebie. Here we have our list of x coordinates and our list of y coordinates. We started out at 0, 0. We move on to 0, 1. Next, we need to move on to the next one, and then the next one, and then the next one. We are also going to keep track of the list of distances in case it becomes useful later. Okay, so here we are looping over each step. So n is going to be which step in the spiral we are currently at. We're looking at how far did we step last time, and then we call our next step function. This is the one that does all of that searching across every possible direction. Then we need to try out the steps that were returned to us. So deltas is the list of possible steps that we might take, right? So we're appending to deltas all of these steps that we might take, where we are stepping one direction along the x, one direction along the y. Of course, we might also try out going in the negative x and the positive y, going in the negative x and the negative y, going in the positive x and the negative y. You get the idea. We've got to try every possible combination of the direction that we might go. So we end up with 8, as we need 4 positives and negatives going in this distance along the x and this distance along the y. Then we need 4 with positives and negatives switching the 2 distances. So there's 8 possible steps we might take. Except there might be more. There is an interesting problem that occurs when you move along a Pythagorean triple. As a reminder, the way a Pythagorean triple works, it is a special combination of numbers where if you move, for example, 3 units along one axis and 4 units along another axis, you end up with just a simple 5 along this direction, along the hypotenuse. That doesn't work for every set of integers because the Pythagorean theorem has a square root, so it does not always return an integer. But if you step 3, 4, you get 5. If you step 6, 8, you get 10. There's other Pythagorean triples I sadly do not have memorized. But this just addresses the question, why would you step 3, 4 when you could just step 5 along one of the axes, right? So 5, 0 might be preferable to 3, 4, but it might not have gotten picked up by the next step function. So this thing might be missing this 5 based on the way it is set up. And so if we have a Pythagorean triple, if we have that integer of this magnitude equals the magnitude, in other words, if this number here is an integer, then we can also append to deltas mag 0, 0 mag, negative mag 0, 0 negative mag, etc. So we at least have 8 possibilities, but we might have 12. Then we have to select from those possibilities based on which step is going to take us in the clockwise direction. So we're going to use the dot product and the cross product to check that out. We're looking for the cross product to be less than 0, and we're looking for the dot product to be maximized here. And so that's going to lead us around to a choice where our delta keeps us moving in a clockwise direction. So we update our position here. We add to our position vector the new change, because all we're really evaluating is a change, and then we add that to the previous position to get the new position. We append our new x value and our new y value, and we append our new distance here, just as the magnitude of the position here. And then we are going to plot it. And so what we're going to start out with is a spiral of 10 steps. This is what we drew on the board earlier in this video. You can see each step is getting longer. It's not necessarily getting longer by an integer, right? Because here we have a length of 1. Here we have a length of square root of 2. Here we have a length of 2. Here we have a length of square root of, let's see, that's a 1 by 3, so that's going to be a square root of 10. Here we got a square root of 13, and then here we finally have a 4, a nice plain simple 4. Somewhere around here is actually one of the first Pythagorean triples that you run into that we have to check against. It did not take long for Pythagorean triple to ruin the algorithm. That's why I had to add that in. Let's see what happens if we go past 10. Let's go to 20 steps in the spiral. You can see we continue on with the spiral pattern here. We ended at negative 8, 6. We ended up somewhere over here last time, so we've continued along here. Again, each step of the spiral gets longer, and we've got to continue going around in the clockwise direction. It's at this point that you start to feel like you've got a pretty good sense of the pattern. Oh, but wait, because this is what happens when you go to 30. Right, we ended around here somewhere at 20. We continue along here. We're continuing to spiral, but then you notice it starts to turn what looks like a little bit early, and then it turns too much, and then it turns way too much, right? If this thing were going to continue in a pure spiral, it can't turn upwards yet. It's got to turn upward, somewhere around here, right? So that it doesn't cut over itself. But it does cut over itself. In fact, it does so rather dramatically because it cuts over itself here, and then it has one of these drastic changes. I think this is where you hit one of the Pythagorean triples or something similar, where you've got an integer distance that you can go that's less than, that's between the distance you get for this angle and the distance you get for the next angle. So it shoots up here instead of continuing along. So not only does it cross itself, it gets this dramatic obtuse turn here and then shoots up, crosses itself yet again, and it looks like it is bound to cross itself here. I'm not going to bother with any more intermediate results now. Let's go along to a spiral of 100 points. This is where it looks like the genie is getting out of the bottle, basically, because we started over here, we spiraled around, we crossed ourselves here. We have now crossed the spiral multiple times. It eventually kind of escapes here on this little trajectory. It looks like it's forming a new spiral. Then it curves back around, crosses itself again, curves back around, crosses itself again. You can probably get the idea that this is going to continue happening. Right, back when we were at this picture, it looked like this thing was going to continue on with a spiral. And so I feel like it really messes with your head when you see this pattern, that it doesn't continue along. It's doing this sort of like loop-de-loop around itself. And in fact, it looks like it's bound to continue crossing itself. If you go up to 10,000 points, this is what you get. So 0, 0, the spot we started in is over here. In like this little densely packed area, we can't even see where the steps are. It keeps spiraling around, crossing over itself, eventually ending up over here. Like there is no way that you could have predicted that it would look like this from those first few steps. It really messes with your head about how patterns form and how predictable mathematics is. And it's such a neat picture here and shows you how you get these really convoluted structures out of such a simple rule that should produce a nice simple pattern, produces this little inky monster here.